So, dear participants, good afternoon, everyone. It is with great enthusiasm that I welcome you all to the final day of our faculty development program. Over the past few days, we have been privileged to learn from a host of distinguished speakers who have brought individual, invaluable insights and expertise to our sessions. Today, as we conclude this enlightening journey, we have an equally exciting lineup of speakers who will share their knowledge and experiences, leaving us with much to ponder and apply in our academic pursuits. So, our speakers today are renowned experts in their respective fields, and we are fortunate to have them guide us through the latest trends, best practices, and innovative approaches that are shaping the future of education. Their contributions have been pivotal in enriching this program, and we eagerly anticipating their final session. Let us approach this day with the same enthusiasm, dear participants, and with all the curiosity that have marked our journey thus far. I encourage you all to engage actively, ask questions, and make the most of these last sessions. Together, let us ensure that this final day is as impactful and memorable as the rest of the program. Without further delay, let's welcome our first speaker of today, Dr. Shubhra Shankar Dhar, who is a professor in statistics at the IIT Kanpur. Nowadays, he mainly works on non-parametric method for infinite dimensional data and topological data analysis. He received C.R. Rao National Award in Statistics in 2019, P.K. Kelkar Fellowship from IIT Kanpur in 2020. Since 2021, he has been Associate Editor of Shankho Series A. So, sir, without further delay, I would like to hand over the session so that we can listen the kind knowledge and the world of wisdom from you. Thank you so much, sir.
Thank you, Anuradha. It is my pleasure to have opportunity to give a talk in this workshop, and the best part is that this is related to AI and ML, which is now I would say that the most fashionable in one of the most fashionable topics in fashionable topics in uh, research community. Everyone wants to work on AI and ML. So although my knowledge is very limited on AI and ML, but I can understand, I can assure you that the whatever I will discuss, that can be thought of as a component of at least ML. I'm not very sure about AI, but definitely from ML points of view, regression problems always can be think about some sort of a learning problem. So in that sense, although it is a classical statistics in some sense, strictly speaking, but in some sense it can be treated as a topic in ML also. Because before starting anything, I just want to say that whenever we discuss about the ML, we generally try to think about typical those who are familiar with statistics literature. Generally, we try to think about that book, a famous book, that Trevor S. Tipsrani books, Elements of Statistical Learning. And Elements of Statistical Learning has a quite a bit exposure on. It has a quite a bit one chapter on, I think, particularly regression problems. And in that sense, regression, you can think about the supervised learning, because we know that there are two types of learning technique generally we consider. One is unsupervised technique, unsupervised learning. That means cluster analysis. And whenever we think about the classification problem or the regression problem, that means it is a supervised learning. That means we know the learning procedure, and whenever the future observation is coming, we can check that whether the future observations falls into the suppose 2-class problem in category 1 or category 2. So in that sense, you can think about, if you don't want to think regression as a topic in statistics, you can think about it is a topic in supervised learning technique. So in that sense, it is relevant in the machine learning conference or workshop. Okay. So now I think we can start. Anyway, this is first word itself is wrong. What I wrote, it is a functional regression. It is not function regression. So functional regression and related research problems. And what is functional regression, that I will come later on. First, I will start with simple linear regression. Then I will discuss multiple linear regression. I believe that both components, I think many of you may know that, but to have, for the sake of completeness, to before moving to the functional regression, we should have a track on the simple linear regression and the and the multiple linear regression. Then this part essentially, this is I forgot to mention, partially this work is a joint work with one of my former student, Pratim Guhaniyogi, who is now postdoc in John Hopkins University. When I was a faculty in presidency, he was my UG student. Thereafter, he did MStat and PhD from Michigan State, and now he is in postdoc in John Hopkins. So last part of the work essentially joined to work with Pratim, and first part essentially it was prepared by myself. Okay. So what I was trying to say that for the sake of completeness, we will discuss a little bit about the simple linear regression, multiple linear regression. Then in that spirit, we will move to the functional linear regression. Uh, I should, strictly speaking, here I should write scalar on functional linear regression. Anyway, that part I will come on later. Okay, so we can start. First of all, I want to discuss the plan of the talk. Plan of the talk is, first of all, I will discuss for any statistical or machine learning problem. I believe that we should have, first of all, the description of the data should be very clear before going to model, before going to discuss deep mathematical properties, everything. Dataset, the description of the dataset should be very clear in our mind. Then I will discuss about the description of the simple linear regression model. Thereafter, it will be a description of the multiple linear regression model. And I will discuss a little bit about the multiple non-parametric regression model. Then essentially the main topic, which is mentioned on the title of the topic, title of the talk, that will come, a description of the functional regression model. And then I will discuss one particular research problem, and of course with the motivation, some idea about the solutions. Maybe that part will be too technical. It may be difficult for many of you, but I will try to I will try to use lucid language as much as possible, and then some related future research problems. Okay, so that is the plan of the talk. So first start with the description of the data and simple linear regression that all of you are familiar. That is, suppose we are having a IID random vectors x1, y1, x2, y2, xn, yn, having the same distribution as xy. Okay, and we are considering a simple linear regression model y equal to beta naught plus beta 1x plus epsilon. Here just I want to mention that here linear is coming in the sense of linear with respect to parameter beta. That means what I'm trying to say that y equal to beta naught plus beta 1 x square is also a simple linear regression model. Because as long as it is linear with respect to the unknown parameters beta naught and beta 1, it is linear. And simple in the sense it is only one covariates. By the way, I should mention that those who does not have statistics background, x1, x2, xn, here it is called covariates or independent variables, and y1, y2, yn is called response or dependent variable. Okay, and this is the model y equal to beta naught plus beta 1x plus epsilon. And if you think about from mathematical point of view, it is the equation of the straight line. Beta naught is the intercept, beta 1 is the slope, and epsilon is some error. Okay. As I said here, beta naught and beta 1 are unknown parameters, and epsilon is a certain random error. Now I am trying to say the model, whatever we have written, y equal to beta naught plus beta 1x plus epsilon, That is a population version. If you look at, there is no I is involved, there is no data is involved, only a random vector x, y. We are having a model y equal to beta naught plus beta 1 x plus epsilon. Now I am saying, given the data I equal to 1 to n,
Sir, sir,
Sorry to interrupt you,
pardon.
sir. The screen is
Your
not visible.
screen, yes, your screen is not visible, sir.
why?
Sir, can you please again share because it is now not visible.
Okay, just a minute. I'm sharing. Yes.
Yes, now it's visible, sir.
Oh, I think something happens. This is also machine learning problem,
This is
AI
a
problem.
yes, sir.
So,
Yes,
so
sir.
whenever
Now it's visible.
it's
Please proceed, sir.
invisible, you just let me know. Okay.
Yes, sir. Yes, sir. Sure. Sir.
So data and sample version of the model, if you think about in the beginning, I didn't write anything about y equal to beta naught plus beta 1 x plus epsilon. We didn't write anything about the x1, y1, x2, y2, x and y. We have written just the random vector x, y. Based on that, we have written the model. But here, whenever we are having the data x1, y1, x2, y2, x and yn, then we have the model yi equal to beta naught plus beta 1 xi plus epsilon I. So that model sometimes we call the data version of the model and sample version of the model. Okay. And now what is our objective? Objective is to estimate beta naught and beta 1 based on the given data x1, y1, x2, y2, x and yn. If you look at very carefully, here I have written small letters x1, y1, x2, y2, x and yn because it is a data. Now, we have the random vectors. I started with the IIT random vectors, capital X1, capital Y1 to capital X and Yn. Those are all function of omega, sample space, elements of the sample space. So we are fixing for a particular omega. So we are getting this data, okay? X1, small x1, y1, small x2, y2, small x and yn. So that part, it is slightly mathematical issues are there. So that part should be very clear in your mind. So your data is x1, y1 to x and yn. Small x1, y1 to small x and yn. Okay. Now, so our objective is that how to estimate the unknown parameters beta naught and beta 1 in the simple linear regression model. And you know a few things. You know few methodologies like least square, least absolute deviation. That I will come to the latter part. Now I want to move to multiple linear regression. Just generalization of the simple linear regression model. Suppose we are having a p plus one dimensional random vector x1, y1, x n, yn. If you look at here, x1, x2, xn are bold facet. Because this is we have written it is a p-dimensional vector. That's why it is written as a bold font. And y1, y2, yn is univariate, so we have written is just simple way, the way we generally write. So it has the same distribution at x, comma y. Here xi, if you look at it, is p component p-dimensional vector, and x is also a p-dimensional vector, random vector. Now we are considering a multiple linear regression model. So y equal to beta naught plus beta 1 x1 plus beta p xp plus epsilon. So if you think about it, is a p plus one dimensional space. And if you look at, this is the equation of the hyperplane. So generalization of the straight line in the multi-dimensional space. Same type of whatever we wrote earlier in the simple linear regression. That is the same thing we have written, but p-dimensional generalization plus some random error epsilon. Okay. And here also, if you look at it, it is simply a population version. Only in terms of x we are writing. So here beta curl equal to, here unknown parameters is beta naught to beta 1 to beta p. So this is the p plus one dimensional vector of unknown parameters, and epsilon is a certain random error. And what will be the data or sample version of the model? Data and sample version of the model, if you think about, again, whenever we are having the data, we should write small x1, y1, small x2, y2, small x and yn. And every small xi is a p-dimensional. And that is the things, that is the way we have written the sample version of the model, that yi equal to beta naught plus beta 1 x1 I plus beta p x pi plus epsilon I, where I equal to 1 to n. Okay. So now again, the objective is to estimate the beta, which is a p plus one dimensional vector based on the given data x1, y1 to xn, yn. What were the methodologies? As I said earlier, there are few well-known methodologies are available in the literature to estimate beta curve. For instance, least square method, least absolute deviation method, AM estimation, L estimation, lasso, ridge regression, elastic net. Those things are very well known in the nowadays in the community. Particularly, least square and least absolute deviation is very classical. AM estimation, classical means I am saying it exists in the literature more than 100 years, maybe almost 200 years. And AM estimation, L estimation techniques also came around 1969, 1970. Lasso ridge regression, they came around 1980s, 1990s. Lasso came specifically 1996. And elastic net is some sort of, you can think about combination of lasso and ridge regression. These are all, if you think about, I didn't describe that all those methods, what is least square, what is least absolute deviation. Whenever I will discuss about the non-parametric regression, I will describe it. But if you think about what should be the strategy, I'm just going back to the last slide. Your model is y equal to beta naught plus beta 1 x1 plus beta p xp plus epsilon. So in order to, epsilon is your error. If this is error part is added with the to the linear regression part. Now naturally your idea will be, if you think about the data version, yi equal to beta naught plus beta 1 x1 I xi1 2 plus beta p xi p plus epsilon I, your idea will be minimize some sort of error. And there are n many errors if I think about from the data version. So some sort of you have to accumulate the all possible, you have to accumulate the errors, and some sort of you have to minimize the errors. So one of the idea is that you can take epsilon I square of the epsilon, and then minimize the summation over epsilon I square. That is the least square method, or summation over modulus epsilon I. Just note that. You can ask me why I'm taking square or modulus. The reason is that epsilon can be positive, epsilon can be negative, and we want to minimize the error. So either we can take the absolute error, absolute norm, or you can take the square, or you can take the whole to the power 4. Anyway, you can take any LP norm. So some sort of, you have to accumulate the all possible, I would say that the all possible errors, and then you have to minimize that accumulated error. So that is the idea. That is the way we landed up to the, say, least square method. Whenever we are minimizing summation over I equal to 1 to n epsilon I square, least absolute deviation. Whenever we are minimizing summation over I equal to 1 to n modulus epsilon I, or something like that. Similarly, from sparseness point of view, people use the lasso, some penalty parameter will be there, ridge regressions are there, elastic net are there. So these are the idea to estimate the beta naught, beta 1 to beta p. Okay, so these are the methods. Now I want to move to the non-parametric regression model, which will give you the idea to before moving to the functional regression model. Okay, so simple linear regression and multiple linear regression, I believe that many of you know. Now I want to move to non-parametric regression model. So first of all, we have to understand what is non-parametric and what is parametric. If you look at the linear regression model, simple or multiple, we are having the parametric form of the regression model. For instance, simple linear regression model, it is straight line. Multiple linear regression model, it is it is hyperplane. Now, in the non-parametric regression model is saying that we are not assuming any model as such, parametric model, that it is quadratic, or it is parabolic, or it is some sort of 5-degree polynomial. We are not assuming anything. We are assuming y and x related by some unknown function m, and then we try to estimate the unknown function m. Okay, m or whatever function you want to call. That is the idea about the non-parametric regression. So what is that model? We are having the, so first of all, let us discuss the data. So we are having the data, p plus one dimensional data, random vectors. I am saying still I am calling it as a random vectors, x1, y1 to xn, yn. I am writing capital because I am calling it as a random vector. Having the same distribution as xy, here xi is p-dimensional vector, and x is also a population which is identically distributed with x. X is also a p-dimensional vector. Now we are writing a multiple non-parametric regression model as y equal to mx plus epsilon, where m is a function, unknown function, which is mapping from Rp to R, and epsilon is a certain random error. So m we do not know. M at most you can assume that m is a suppose m is a twice differentiable function. You can put some assumption on the smoothness of m, but you do not know the exact form of m. Okay, we have to estimate the m from the data. That is our main objective. Earlier cases, in the linear regression or multiple linear regression cases, our objective was to estimate the unknown parameters beta for a given data. Here there is no unknown parameters, although it is a wrong statement if I say there is no unknown parameters. M also you treat as an you may treat as an unknown parameters, but here it is an infinite dimensional unknown parameters. Earlier, if you think about, if you can recall, in the simple linear regression model, your unknown parameters was 2-dimensional, beta naught and beta 1. Multiple linear regression model, your unknown parameters was p plus 1 dimensional. But here also you can think about, you have an unknown parameter m, which is infinite dimensional because it is a function. Okay. So we want to estimate that either you can call it as an unknown function, or you can think about you want to estimate the infinite dimensional unknown parameter. Now the data or sample version of the model is yi equal to mxi plus epsilon I equal to 1 to n. Okay. So again, I am assuming that the data is, you have understood what is data. Data is your x1, small x1, y1 to small x and y, small x2, y2 to small x and yn. Yes, I have written the data. So this is our main objective. So how to estimate the m? Let's discuss about it. So for without loss of generality, we are considering p equal to 1. Then p for general p also you can consider, but it will be notationally challenging. That's why, for sake of simplicity, we have considered p equal to 1. Now, if you look at the model y equal to mx plus epsilon, and if you assume expectation of epsilon given x equal to 0 almost surely, those who are not comfortable with almost surely, just you consider expectation of epsilon given x equal to 0, then expectation of y given x equal to mx. Okay, so this is the way we can think about expectation of y given x equal to mx. And if some of you have statistics background, if you can recall, in the BSc first year or second year, whenever you first time learned the regression analysis, also definitely you learned in two ways you can define the regression model. One way is that the way today I have defined, directly from the model. Another way also you can define, at least mean regression case, that the expectation of y given x equal to beta naught plus beta 1x. Just go back to the first slide. I'm going back to you. It will be clear. It should be very clear. Your model is y equal to beta naught plus beta 1x plus epsilon. If expectation of epsilon given x equal to 0, then you can think about, you can define the model in this way, that your simple linear regression model expectation of y given x equal to beta naught plus beta 1x. So that is the way also sometimes, often, I think many of you may learn, might be learned in this way also, linear regression model. So, the uh, for the non-parametric regression case, we are assuming mx equal to, we are defining the linear regression model mx equal to expectation of y given capital X equal to small x. I just want to say that since it is the model mx is regressed with the conditional expectation, that's why you can think about it is some sort of mean regression. You can consider with the conditional median also, then it will be a median regression. But I don't want to go that part, that the median regression, trimmed mean regression, mode regression. That part may be very difficult for few of you, but I'm just wanted to say that for the mean regression, this is the way we can characterize the regression model, expectation of y given x equal to mx. Since if we assume, I should not say since, if we assume that expectation of epsilon given x equal to 0, for technical point of view, I can say up to almost sure is good enough. We don't need even point-wise. Now, suppose MN at what is our objective? On the last slide, we mentioned that our objective is to estimate the unknown function M, or we can call unknown infinite dimensional parameter M. So we are denoting this unknown infinite dimensional parameter as a MN hat X. N suffix is coming. The reason is that it is a data. It is a data dependent. Whenever you are having the estimator depending on the data, and sample size of the data is n, so it should depend on n. So mathematically, for to be precise, mathematically I would say we should write n. So m at n x essentially estimating the expectation of this conditional expectation. And what is the definition of conditional expectation? I think that all of you know, that is integration y into conditional density function. And that we have written that suppose gxy is the joint density function of xy and hx is the marginal density of hx, then joint by marginal is conditional density, and integration with multiplied by y. This is the simple definition of conditional expectation. And then conditional expectation we are estimating in this way. If you look at the integration, uh, G is unknown to you. Conditional density, you have to estimate the joint density G is unknown to you. The marginal density H is also unknown to you. So estimating expectation of Y given X, in other words, estimating MX, is essentially boils down to estimating the joint density and the marginal density function. Now, many of you may know or may not know, there is a long literature on the density estimation, probability density estimation. That people may use many techniques. Here we have used kernel density estimation. That I am not going into that part. It is a separate topic altogether. So I'm just telling you, using kernel density estimation technique and some light mathematical conditions, I'll give you the notation, meaning of the notations. Ultimately, mn hat x will be summation over I equal to 1 to n, this type of form, where k dot is a probability density function and hn is the sequence of bandwidth such that hn tends to 0 as n tends to infinity. So if you look at, this is your mn at x, it is nothing but the expectation of y given x, which is nothing but the integration y into joint density divided by marginal density. We are plugging the density estimator of G and H, and then after doing some algebra, quite a bit long algebra and few mathematical conditions, then we are having ultimately very simplified form. If you look at mn at x equal to summation over I equal to 1 to n k of k into yi divided by summation over k. And what is k? K is certain probability density function. And you know, I believe that what is probability density function? It is non-negative, and integrate over, that will be equal to 1, integrate over the support. So this is the mn at x. So just try to think about, after doing I skipped the algebra. Algebra was quite a bit long algebra, but all those things, conditional expectation, everything, ultimate form of the final form of the MNATX is very simple. It is simple weighted average. If you think about, you can treat it as a summation over I equal to 1 to n Wi OII divided by summation over I equal to 1 to n Wi. And Wi is nothing but the k evaluated at the point x minus xi divided by hn. And this is well-known Nadaria-Watson estimator. And Nadaria-Watson estimator, and this estimator was proposed in separately by Nadaria and Watson. Nadaria's proposed in 1964 or 5. Watson also proposed at the same time. And Nadaria's paper appeared in Theory of Probability and its Application. It is now Siam Journal. Maybe some of you know Theory of Probability and its Application. And Watson paper, as an Indian, we can be proud. It appeared in Sonka series A. So where I am now associate editor. So it appeared in 1964. So this is famous Nadaria-Watson estimator. Now, the reason I wanted to discuss the non-parametric regression, the reason is the following. The reason is that ultimately we have seen that after all those things, whatever it is complicated or simple, that is a separate secondary issue. But ultimately, MNATX is nothing but the weighted average. And you know, weighted average is nothing but you can think about as a minimization problem. If you suppose you have the data x1, x2, xn, and during our high school days, we have learned the definition of average. Average is nothing but the 1 by n summation over I equal to 1 to n xi. That is the average that we learned during our high school days. Now, when we became to the college student, UG student, we learned that average is nothing but the minimization of summation over I equal to 1 to n xi minus theta whole square. If you have the data x1, x2, xn, if you minimize summation over I equal to 1 to n xi minus theta whole square, the estimator of theta will be, by simple calculus, you can see that it will come out as a average. That we learned during our first year UG days. And moreover, if you minimize summation over I equal to 1 to n xi minus theta whole square wi, hello, excuse me, just a minute. Sorry, I am extremely sorry. Someone is knocking at my office door. So K dot is a probably sorry. So instead of the
Sir, it is
average.
all right, sir. Sir, please proceed. It is all right.
So if you have the average instead of simple average, suppose you are having weighted average summation over wi yi and summation over wi equal to 1. Nowadays, after COVID time, we have heard a lot about weighted average. So in that case also, you know that this is weighted average can be treated as a minimization problem. Summation over I equal to 1 to n yi minus theta whole square wi. So since it is a weighted average, so you can always write down as a minimization problem that MNATX equal to arg mean of 1 by n summation over I equal to 1 to n yi minus theta whole square, and this is your weight. K part is your weight. K evaluated at the point x minus xi divided by hn. Now you may ask me one question that why did I write 1 by n? 1 by n I wrote for a particular technical reason. That is again, it will be related to probability theory, related to weak law of large number. Using weak law of large number, I can explain because apparently, if you look at we are minimizing with respect to theta. So having 1 by n or not having 1 by n should not have any problem. It does not have any problem. Forget should not have. It does not have any problem. But we are writing, the reason is that it will give you some sort of stability. If you prepare your own code to minimize this problem, if you don't write 1 by n, you will see that it is getting exploding. So it will be getting exploded. So in that case, just for stability purpose, using weak law of large number, I can explain to you that we should write 1 by n. But if you don't write 1 by n, that is also okay in terms of minimization problem. Now, the point is that this Nadaria-Watson estimator, famous Nadaria-Watson estimator, if you look at, we are writing in this way, this minimization problem. What we are doing, if you think about this minimization expression very carefully, yi is your data, xi is your data points, x1, y1, x2, y2, xn, yn is your data points, and theta is a constant. So you are, and x minus xi, hn is a very small quantity, which is tends to 0 as n tends to infinity. That means you are trying to estimate yi locally by a constant theta. And that's why Nadaria-Watson estimator, sometimes it is called local constant mean estimator. Mean is coming because we are estimating by expectation of y given x. That's why it is coming conditional mean. In that sense, we call it as a mean. And since it is written as a yi minus theta, so it is local constant mean estimator. I just want to mention you here, I didn't mention, you can be approximated by local linear also. You can be approximated by local quadratic also. And the best part is that, suppose I'm giving you the example local linear. So that will be yi minus theta naught minus theta 1, x1 minus, suppose, x minus xi. So in that case, theta naught plus theta 1 into x, that is a linear equation. Now, estimate of theta will give you the estimator of m, and the estimate of theta 1 will give you that estimator of the derivative of the m. So this is the great, I would say that the main crux of this type of problem. As you increase the order of the polynomial, your you can estimate the corresponding derivatives of the regression function also. Okay, just a minute. I'm just some work is going on. I'm just telling them to stop it. Just one minute. The meeting is going on. I'll stop that. Sorry, someone is working, so sound is coming. That's why I. So is it okay? So this is the Nadaria-Watson estimator, the concept of local constant estimator, and you can use local linear, local quadratic. Accordingly, you will get the estimator of the corresponding derivatives as well. Now, this idea will use in the functional regression or our main research problem also. So I just want to discuss a little bit about the functional regression also, because otherwise we will not able to explain the research problem. So again, so what we have learned today, we learned simple linear regression, we learned multiple linear regression model, we have learned multiple non-parametric regression model, although derivation we have done for p equal to 1, that means simple non-parametric regression model. Now I want to move to the functional regression model. Suppose we are having again the IID random element x1 y1 to xn x2 y2 xn yn, having the same distribution as xy. Here we are considering x is an infinite dimensional element. X is a L201 valued random element. What is L201? That means integration 0 to 1 x squared t dt x squared t with some measure, say mu t, that is finite. That is called that. In that sense, I am saying it is L201 valued random element. And y is a real random variable. Y is a real random variable. If you are not comfortable with L2, at least you can assume that x is a function. Here x1, x2, xn itself is a function, and function defined on the interval 0 to 1. A data is a function in the sense, if you think about, I should give some practical real life example. For instance, whenever we are having univariate data, our blood pressure, okay, our blood pressure, the upper one, suppose our blood sugar, suppose HB1AC, this is our univariate data. 100 people are there, they are HbA1c measure. This is univariate data. But we are checking blood pressure and blood sugar also. Then it is a multivariate data, every person. Now, what is the example of the functional data? That means infinite dimensional data. If you think about, suppose we are having 50 people in a room and we are doing our ECG for some cardiac reason. And ECG curve, so every person will get some curve. Your case, your ECG will have few curves, my ECG will have some few curves. So if you look at, every observation is a curve. Okay, in that sense it is a functional. So that means data itself is a function here. Or if you think about the rainfall data over the years, and we are measuring the rainfall on every day for 365 days, and we are having choosing the 4 cities, suppose Kolkata, Delhi, Bombay, and Chennai. Okay, so 4 cities, 5 years rainfall data. So every year we are getting 365 points average rainfall. So we can interpolate by a function. So essentially, this will be an example of the functional data. So you can embed into the, suppose, L201 valued random element, and y is a real random variable. Now I'm defining, as I said, that strictly speaking, the name of the talk, title of the talk should be scalar on functional linear regression model. We are considering a functional or linear regression model, y equal to alpha plus integration 0 to 1 beta t xt minus expectation of xt dt plus epsilon. So this is my population version. Where it is, what is unknown parameter? So xt and y is your random element. X is L201 valued random element, which is a function, and function index function is, here function parameter is t and time parameter t, and y is a scalar valued random element, and alpha is one unknown parameter, which is essentially the intercept. So what we are thinking in the infinite dimensional space, we are thinking some sort of infinite dimensional hyperplane, and coefficients are also function. If you look at here, unknown parameters beta t are also function. So beta t are infinite dimensional parameter, or you can think about functions. Alpha is a scalar valued unknown parameter. Alpha is just a unknown unknown intercept parameter. So in this problem, our objective is to estimate this unknown parameter beta and alpha, where alpha is scalar valued, beta is infinite dimensional valued. Now data version, what is data version? I equal to 1 to n xit minus expectation of xt. Expectation of xt is a non-random quantity. It is a deterministic quantity. And given the data y1 x1, y2 x2, y3 x3, if you look at, whenever I'm writing x1, x2, x3, it is a function t, because it is L201. So this is the data and sample version of the model. So as I said, the objective is to estimate the unknown parameters alpha and beta based on the given data x1, y1, x2, y2, xn, yn. So how to estimate those unknown parameters? So we need to know some techniques. First of all, we are defining V T1, T2 equal to covariance x1, x2. T1 belongs to 0 to 1 and T2 belongs to 0 to 1. Now there is a well-known mathematical results. Many few of you know that if it is an L201 space, we have the Mercer's theorem. It will give orthogonal expansion, and this is here. This is the expansion VT1 VT2, that is R equal to 1 to n lambda xi r T1 xi r T2, where lambda xi r is the set of the eigen components, and which is converges in the sense of L2, means VT1 minus VT2 minus summation over R equal to 1 to some capital M. If you take whole square, integration dt1, dt2, that tends to 0 as m tends to infinity, capital M tends to infinity. So that is the meaning of L2 sense. Similarly, using similar type of expansion, it is called Karhunen-Loeb expansion. But recently we have found that Kosambi first time introduced this expansion. This is due to the same, this type of expansion. We are having beta t, which is belongs to L201. It has also orthonormal expansion. Similarly, xt also has an orthonormal expansion, and where br and xi r are the coefficients of the expansion. And hence, since xi-r's are the orthonormal value, just simple algebra will give you BR can be written as the coefficients of the beta t, which can be you can obtain using this one integration 0 to beta t phi r t dt, and xi-r equal to this one. Now all those what is called uh, this beta t xt, all those expansion, just one line or couple of lines algebra, ultimately it boils down to, it will reduce to equation like y equal to alpha plus summation over r equal to 1 to infinity br xi r plus epsilon, where xi r's are uncorrelated random variables with variance lambda r. Lambda r was this one, I think. Uh, lambda r was the from the Mercer's theorem we had the lambda r's from the, if we do the covariance expansion. Now the interesting part is that the model is similar to, it looks like multiple linear regression model, although it is not multiple linear regression model, because here there is no covariance. It is just we have to estimate some different way. Now, how to estimate all those things? So ultimately, it boils down that we have to estimate xi r and beta r, and given the data, we have to estimate alpha as well. So if your VT1, T2 was a covariance kernel, so we can estimate through in this way that the V at T1, T2 equal to this one. Then it has the sample analog of the Mercer's theorem, and this is the again sample analog of the, you can think about the sorry, I should not say sample analog of the Mercer's theorem. It is the the implementation of the Mercer's theorem on the sample analog of the VT1 T2, and similarly it is an implementation of the Kosambi-Karunelloev theorem on the beta hat T, sample version of the beta hat T, which is nothing but the B hat, B R hat and xi hat T, which is we are taking some up to kappa n tends to infinity as n tends to infinity. And what is BR hat? BR hat is, this is the formula, and xi r hat is also, this is the formula. So this is obtained from simple, just very simple way. You can just minimization problem will give you BR and xi r hat. So now we are having beta hat T is known to us. And what was our objective? If you go to the functional regression part, we should not lose the track. Our objective was to estimate beta t and alpha. So beta t now estimated by this way, beta hat t equal to this one, where BR hat and xi r hat is known to you. You just try to think about uh, we are having the data x1 y1 x2 y2 xn yn. If you look at the expression of BR hat given x1 y1 x2 yn x2 x1 y1 x2 y2 xn yn, you can estimate BR hat because here yi is known to you and xi r hat you can estimate from the data. So we can estimate beta hat t, and the model whatever we had, this model y equal to alpha plus summation over r equal to 1 to infinity br xi r plus epsilon, given that we are having y at equal to alpha y bar minus summation over I equal to 1 to infinity. That is the way, if you can recall, those who are familiar with linear regression model, that is the way we estimate the intercept parameter of the linear regression model. So this is the things just I want to discuss, how to estimate the unknown parameters of the scalar on functional regression model. Just one line I just want to mention that I think those who are interested about it, you can consider function on function linear regression model. Then y will be also a function. Here y is a scalar, x is function. But if you want to consider more general function on function linear regression model, then you can treat as a y is also a function. Now I want to discuss a small research problem, related research problem, and this is the part I worked with Protein, and we'll use the techniques of whatever today we have learned. Suppose we are having the two independent data set, YSI and XSI. Okay, S belongs to 1, 2, two independent random samples identically distributed to YS and XS. And we are having the model this one. Already we are familiar with this model. We want to estimate, we want to check, suppose the slope parameters, beta 1t, beta 12 is the slope parameters with respect to the first sample, and beta 2t is the slope parameter with respect to the second sample. If you look at the notation, here s equal to 1 and 2. So s equal to 1 means beta 1t and s equal to 2 means beta 2t. And we want to estimate this, essentially we want to estimate, we want to check whether there exists any transformation G uh, uh, such that beta 1t equal to G beta 2t. You can ask me one thing, yes, it is mathematically fine that it is a mathematical formulation, but why you are doing this test? Any real life application? Yes, there are plenty of real life application. I can just tell you one real life application, very well known. It appeared in Nature a couple of few years back. We are having G7 countries, and G7 countries, there are a lot of literature, a lot of discussion going on G7 countries pollution level. Now in India also, many of us every day we check our AQI level in the city or wherever we live. So the idea, the perception was that it came out in Nature that in G7 countries, the life expectancy, the pollution level has some sort of quadratic relationship. It is not, if you do the functional regression, the parameters, if you consider G7 countries and non-G7 countries, then there is a quadratic relationship. And there are many other applications also, this type of relationship, that if you have two sets of functional regression, one set of parameters may be function of another set of functional parameters, unknown parameters. So these facts motivated us to consider this particular research problem, that we wanted to check whether there exists some unknown function G such that beta 1t equal to this one or beta 12 t is not equal to this one. So the way we have written h naught beta 1t equal to G beta 2t for all linear transformation, and against H1t, beta 1t equal to G beta 2t for some non-linear transformation. For some means we wanted to in the existence of the non-linear transformation. Since we are dealing with non-linear, linear, non-linear, so we wanted to characterize the quadratic part. So we define a class of function G, C is such that collection of G such that G double prime U equal to 0 for all U belongs to V1 and V2. V1 and V2 certain interval. This is just certain interval. And alternatively, equivalently, we are writing this hypothesis problem as a G belongs to C V1 V2 against G does not belongs to C V1 V2, and V1 V2 is specified as the minimum over the beta 2t and V2 is maximum over beta 2t. Now, as I discussed, first 1 hour, first 14 minutes or so, that we know how to estimate beta hat t from the functional regression. So here also, here you are having two set of functional data, two set of functional regression model, and both set of function we are estimating beta 1 hat and beta 2 hat, and then we are having the model, say beta 1 hat t equal to G beta 2 hat t plus some eta j. Okay, and if you look at here, t belongs to 0 to 1. So we are taking arbitrarily points between 0 to 1. We are writing t1, t2, tmn. So m many points, m may also depend on n, your sample size, original sample size. So that's why model is written uj equal to G beta j plus eta j, where G is that unknown function described in the hypothesis H naught. Now using the data uj vj, essentially beta 1 hat and beta 2 hat, we estimate the second order derivative of G based on the well-known local polynomial approach. If you can recall sometime just a while uh, uh, to a few minutes back, we discussed about the local constant approach whenever we discussed about the Nadari-Watson estimator, and I discussed about also the what is called the if you consider instead of local constant local linear, then we'll get the estimate of derivative. If you have the local quadratic, then we'll have the estimate of double derivative. So since C V1 V2 is essentially the double derivative of G, we wanted to estimate the double derivative of G. So we use that same technique, well-known local polynomial approach, and let the second derivative of G is this one, the denoted by the hat of G double prime hat, but the technique is whatever we have discussed, the local polynomial approach. And then we are proposing the test statistics supremum over this one, because if you look at, we had to take care for all. To take care the for all, we had to consider the supremum over U belongs to this one. So this is the test statistics. And then we considered many complicated mathematical assumptions. And after all those assumptions, I just want to tell you, we have proved that uh, after some normalization, mn into hmn to the power whole to the power 5, this tn minus t is your population version. If you look at, this will converge to a supremum of certain Gaussian process. That's result we have proved. It is extremely technical result, and proof is extremely long proof and complicated proof. So these results we have proved, and we have done in this work. It is available on archive. You can, if you want, you can take a look, and we have proved that all those things. That means how to implement this technique on the real data, bootstrap version of the proof. Everything we have done on the paper, on the archive, it is available. So these results is the one of the key results, but not only this is the only result. And we have done many simulation study and the what is called the real data analysis. All those things we have done, and we have seen that this procedure is performing reasonably well. So that is the things, that is the main results. And then I want to discuss that some future direction. Whenever we did this research problem, we always considered errors are IID, but errors can be dependent also. That part, it is in our mind. We can do for the quantiles of the slope parameter. Maybe few of you may know the quantiles, but if you don't know, you can ignore, no issue. Quantiles is another concept in statistics. And also, as I said, that that part I have discussed, that response we have considered scalar, but response can be also functional. So this problem we can do for the functional on functional regression. I think that's all from my side. So thank you. Hello.
Yes, sir.
So is it? So it is okay. So should I stop? Should I stop sharing the uh, slide, or I should it should be on the screen?
Sir, it is all right. I mean, if you have finished your lecture, then I will, take control.
Okay. So I have finished. But
Okay.
I'm ready to
Yes,
take
sir.
any question.
Yes, sir. Yes, sir. Actually, participants, if you have any queries, please feel free to ask, sir. Sir will gladly answer all the queries.
At least first part was, I believe that it is not difficult to understand. Maybe the second part is slightly complicated.
Dear participants, please ask any questions if you find exciting.
Hello.
Yes, sir. Sir, I
Okay.
think, yes, sir. Sir, I think they are very much engaged through your deliver of speech, because this is a kind of, a new domain, I can say. Yes, as you have just spoken that for the second part is maybe a little bit, higher order for some of the participants, since we have the participants from the management field as well in this
But they know
FDP.
their linear regression, I believe.
Yes, but linear regression, and these are the things which they know. So, if sir, it would be very great if you can provide any one or two papers, research papers, so that they can go further, after the this engaging session.
No, no, that's definitely I will do. But I can tell you, I can. You have the my, I think file, the file I have shared with you most likely couple of days back.
Sir, I will check, sir. I will check, and
Yeah,
if it is so,
that one I sent to you. You can check it. I sent to you. So you can share with them. If they read again and again, they will understand, I
okay,
believe.
sir. Sure,
I believe.
sure, sure,
And definitely
sure,
they
sir.
know the linear regression. The idea is that from linear to non-parametric, we can go some parametric to non-parametric. And main idea is that the data itself can be function. Data
Yes.
doesn't mean that data is always a point. Data itself can be function. That is the main idea.
Absolutely, sir. So, sir, on behalf of everyone present here, I extend our deepest gratitude to you for your invaluable contribution to this faculty development program, and your session on non-parametric regression and functional regression as well have been nothing short of extraordinary. So, your deep understanding of these complex topics, coupled with your ability to present them with such clarity and precision, has left a lasting impression on all of us. So I would request all the participants once again, if they have any kind of queries, they can ask. Otherwise, I will
Or they
just
can drop me an email also. Don't.
yes, sir. Yes, sir. Sir, I will share your email ID as well with the participants so that they can further contact with you. And on this note, I just take 2 to 3 minutes from you, sir, so that I just request all the participants to just switch on their camera so that I can take the attendance of this today's session. Participants, please turn on your camera for today's this session's attendance. Thank you so much. You can switch off your camera right now. So participants, I am extremely happy and glad to see that during this such an engaging semester exam is going on in all over West Bengal and some other places as well. Still, you managed to join in our FDP to listen to some break through research work from Sir. And Sir, on behalf of Netaji Subhash Engineering College and Applied in Electronics and Instrumentation Engineering Department, it is my great and humble gratitude to you for your time, effort, and this engaging, brilliant session. Thank you so much, sir.
Thank you. Thank you. Thank you. Okay. See you. See you. Okay.
Okay, okay. Thank
Okay.
you so much, sir.
Bye. Bye.
Bye, sir.